your oral microbiome is directly connected to your heart disease, is connected to your diabetes, is connected to neurodegenerative diseases, especially Alzheimer. We as humanity would wipe out the cancer from the human body.
Naveen Jain, welcome back to the show.
Well, first of all, this is one of the few places I come back and just have such great memories.
Dude, it's a lot of fun anytime that we get to spend time together, especially I'm so obsessed with the same thing that you're obsessed with, which is the microbiome. And I want to ask, of the healthy foods that people think are making their life better, what should people actually be avoiding?
Well, the interesting thing is there's no such thing as universal healthy food.
No such thing as universally good,
Well,
but what about universally bad?
So universally bad is absolutely true. So for example, sugar is just bad for everyone. There is no one who would say...
Because it's refined, or like in a natural state would we be okay?
In a natural state, it is much better, but especially in the processed state, and there are many reasons. Obviously, is starting from the top of the tube, your digestive tube in your mouth. Every time you eat something that has processed sugar or even sugar, your oral microbes actually use that to produce lactic acid that changes the pH of your oral microbiome. And now, as we are learning, similar to like you and I were obsessed about gut microbiome, in the last 2 years, what we are learning is your oral microbiome is directly connected to your heart disease, is connected to your diabetes, is connected to neurodegenerative diseases, especially Alzheimer. Right?
Really fast, and I do want to get into the actual foods that people need to be avoiding other than sugar, but give us a quick primer on the enteric nervous system. So I've heard you say that we're a donut with a tube through it.
That's right.
Which I think will hit people very strangely, but what is the enteric digestive tract?
Right. So your digestive tract, as you can imagine, starts from the top of the tube in your mouth. So that's where you start the things. And I don't know about you, my mom used to always say, eat slowly, chew your food. And I always wondered, why is she worried that some other food is going to get stuck in my throat? Well, it turns out she must have been a scientist, because when you chew your food and eat slowly, your microbes in your mouth, the oral microbiome, is starting to pre-digest the food so the nutrition can be absorbed in your digestive tract.
So there's signaling going on between the oral microbiome and the microbiome in your gut?
Well, more than just the signaling. First of all, the microbiome itself is pre-digesting the food, and it's sending the signal to the body, the different organs.
Through the vagus nerve?
Through the metabolites that it releases, right?
So wait. You're saying that as I'm chewing, I'm breaking down the food into metabolites.
That's right.
Those metabolites are beating the food to the digestive tract?
The microbiome poops out, the metabolizes, which is microbiome.
But do they do it that fast that as I chew, I'm already sending signals?
Already sending a signal to pancreas. So every time you eat food and it's sweet, it sends a signal to pancreas, hey, the sweet stuff is coming, the sugar is coming, you start releasing the insulin. And when you eat artificial sweetener, guess what happens? The insulin is all there, but the insulin has nothing to do because there is no glucose to process. And now the people who eat diet stuff, diet soda, diet stuff, thinking they're doing good, and now they become insulin resistant. They end up getting diabetes because they're taking a lot of the artificial sweeteners.
I want to get back to that because anecdotally is the only thing I can speak to. That didn't seem to be my experience, but let's set that aside. So I'm chewing something, I'm sending a metabolite-based signal to my digestive. So I'm pre-digesting it and sending a metabolite-based signal down to the gut.
Gut and the rest of the body. Remember, the blood carries the stuff that metabolites are absorbed by the blood. So as soon as they're absorbed, it's sending the signal to the whole body. Right? Now, in addition to that, your gut is also sending the signal through the vagus nerve to the whole body, right? So if you look at we as humans, we are really a super organism where 99% of all the genes that are expressed in our body are not our own. They don't come from our mom and dad. They actually come from these microbes that are in our mouth, in our gut, in our eyes, on our scalp, on our skin, and literally everywhere. And these microbes and us are in symbiotic relationship. And when that relationship gets broken is when your body is never at ease, and we call that dis-ease is disease.
Okay, so do I have a microbiome in my stomach?
Oh, that's right. Of course, your microbiome is all over your digestive tract, especially the 95% of that is in your gut or colon.
Well, yeah. So the gut, I know.
Yes.
I wasn't sure if in the,
the
acidic level of the stomach, we also have a microbiome.
So there is up in the small intestine, there is microbiome.
Okay.
And then there's literally all through the tract. And obviously stomach has very high acid. But a lot of the people who take these proton pump inhibitors like Nexium, that now allows all the oral microbiome. We're swallowing, give or take, about 1.5 liter of saliva every day. And now that saliva, when it goes to the stomach and there is no acid because you're taking proton pump inhibitors, now all those microbes are going to the gut where they don't belong. And some of the stuff, at least the research shows, the Fusobacterium nucleatum, which is actually an oral microbiome, is #1 culprit for things like colon cancer.
The #1 culprit for colon cancer starts in the mouth? That is shocking, to say the least. Okay, we're going to get to cancer later. Okay, so I wanted that quick primer. You've got all these microbes. They start in your mouth. You have a tube that runs from your mouth through your stomach down into the small intestine, large intestine, colon. We have an ability to break those nutrients down through the digestive process. The microbes also, as you said, poop out metabolites that we then absorb into the body. So we actually want these things. Why is it, going back to the foods that we shouldn't be eating? So we have sugar as a universal, but there's probably caveats on that. But are there other things that are universally problematic?
It's anything that's a processed food in general, that's not something that human body was designed to.
Because the ratio is wrong? Because the chemical substrate gets altered? Like, what is the problem?
So for example, like when you eat wheat, right, it has a lot of fiber in it. And now if you remove everything, all you're really getting is the processed part, right? Which is just the part that normally would be, in addition, if you had it mixed with fiber, will be easy to digest and probably would be...
I think wheat might be the perfect case study to break this down. So I have a feeling as we talk that we're going to find that there's a lot of things that have happened that create the modern dis-ease.
That's right.
Let me use wheat and tell me where I go wrong.
Sure.
So, one, we have to start with the soil.
Yes.
So we've been doing monocrop. We've been putting
fertilizers and pesticides.
Pesticides, that was the word I was looking for. So we're destroying the soil.
Yes.
The
microbiome of the soil, just to be very clear.
Right, the bacteria, the viruses, the phages, which we should talk about phages. I did some research on that in anticipation of this. We're creating a problem at the soil level. We're also genetically engineering the wheat to be higher yield, to be more resistant to parasites, to be able to handle a larger dosage of pesticides, so on and so forth. And for whatever reason, gluten, at least in the US and other countries that use similar farming techniques, have now become really problematic for a lot of people because they break the epithelial lining for people keeping score at home in the gut, which allows direct permeability between what should be a tube, allows actual proteins to make their way into the bloodstream.
Or by the bacteria into the bloodstream.
So what's the bigger problem? I've always thought it was the protein, because with gluten in particular, gluten looks like a piece of the hypothalamus, if I remember correct, a part of the brain anyway. There's a protein made in a part of the brain that looks exactly like the protein in gluten, and that's part of why people get quote unquote brain fog.
It's not as simple, right? So in some sense, there are some people who may actually have a celiac disease, right? There the gluten does havoc to them, right? In general, if you think about gluten, there are about 1.4 billion people that live in India, right? They all eat gluten. So it's not that gluten is good or bad. There are a couple of problems. How it is grown, and also how your microbes actually metabolize that, right? So let's step back for a second and let's look at the human body, and then we'll come back to specific, because I think we dug too deep too fast. So let's back up for a second and let's just start and say, we as humans co-evolved together with these microorganisms, right? So as I was saying that, one could argue that even within our cell, we have these organelles, which are really like cytoplasm. You look at the things like mitochondria. So mitochondria has its own DNA, which is separate from our human DNA, which is separate from the microbes that we are talking about. It's in fact our human cells are multi-organism. You would argue that in ancient cell, these were different organisms that actually all got captured inside the same cell. So we are really symbiotically made there. And then we looking at the complete as a super organism, we're consisting of 99% of all the genes that are coming from all the microorganisms we talk about, right? 70% of our immune system is along our gut lining. Our microbes and our human immune system is constantly interacting with each other. In fact, so much so when the baby is born, our microbiome is constantly teaching the immune system what's a friend, what's a foe. The fact is, why is it there's so many trillions of these bacteria can live inside us and our immune system is not killing them? Why is that? Because if they think they are foreign substance, you will have a constant inflammation, the constant bombardment of the things trying to kill them. What's happening is, as the baby is born, these organisms are starting to tell immune system, we are part of self, don't need to get paranoid, we are all working together. And then we together will detect when there is an attack on us, the pathogen that's coming from outside, and then we can actually work together. In fact, when the baby is born, the first few days, as I think we talked about last time, the first few days of mother's milk contains oligosaccharide, which is literally a fiber. The oligosaccharides cannot be digested by the human body. It can only be digested or fermented by the microbes in your gut. And that through that, the microbes are releasing butyrate, which are actually the short chain fatty acids that are anti-inflammatory. So imagine what nature is saying. Nature is saying, we just created this offspring. To keep this offspring healthy and growing, we shouldn't be necessarily feeding it. You need to be feeding them to make sure that we are all together. And then as you start to look at the first exposure to the microbiome, it starts in the birth canal. So when the baby is being born, it's bathed with the birth canal, so vaginal microbiome. And that's really the first exposure you start to get. And then as we start to grow, you could have identical twins, you still have different diseases in different twins, right? And we'll come back to it in terms of why the DNA that people say your genes are your destiny, why that is completely wrong, right? But we'll get to it in a second here. So coming back to the human primer, we really are a super organism that are symbiotically working together. When the relationship gets broken and we are not feeding these microbes what they need to survive, they start to scrounge around and they're starting to now do different things. Their behavior completely changes. So it's not the organism change, what functions they perform is constantly changing. Right? So same organism can produce something good in one environment, your gut environment, and the same organism in my toxic environment could produce something totally different to survive. Right? So what happens is people take these probiotics, like Akkermansia is a great example. A lot of people take Akkermansia thinking it's good for you. That is the number one organism. If you Google Akkermansia and MS, that's the number one organism that's directly connected to causing MS. So why is it? In some environment, Akkermansia produces good stuff like
short chain. Do we know what environment is positive and what's negative?
Yeah, and it's actually, so when you have the inflammation in the gut lining, remember Akkermansia's full name is Akkermansia mucin-phila.
I love that you said remember. I had no idea.
Yeah.
But
yeah, so lover of mucin.
Really?
Okay. Mucin-phila is a lover of mucin. So it really lives in your mucin. And when you are essentially have high inflammation, or you let's assume go on a long diet that you're not eating food, you go on a 3-day fasting, it starts to eat your mucin. Right? And now all the barrier that we had created is gone. Your gut lining can get permeable. So your gut lining gets permeable because there is inflammation. What causes inflammation? Your microbes are producing things like lipopolysaccharide, LPS, high amount of protein fermentation causing producing ammonia, or high amount of food that's producing a lot of sulfide, a lot of flagellar assembly, a lot of the stuff that's going on that's highly toxic. That causes the inflammation in the gut that breaks the boundary, that breaks the intestinal barrier to be permeable, and then not only the food starts to go, the bacteria start and the viruses start to now translocate into the blood, causing a systemic inflammation. And by the way, same thing happens in your mouth. When you have a bleeding gums or leaky gums, just like a leaky gut, you have leaky gums. Guess what? When it's bleeding, all the microbes from your mouth are going into the blood, causing the same systemic inflammation. And that's what causes the systemic diseases in different organs.
Okay, so now that we have that set up, let's go back to wheat.
Wheat, yeah.
So there's a lot of things that have happened in a modern context that alter the way that we respond to wheat. What is the bigger problem? And look, I get that this stuff is all so intertwined, but you hear a lot about, well, if you eat bread in Europe, you're not going to have the same negative inflammatory response you're going to have if you eat it here. So is the bigger problem that a modern diet is changing the makeup of your microbiome, or is it that we've altered the food substances themselves, that even if you were eating the same thing that your ancestors ate long ago, that you'd still have a problem because of what we've done to the soil, genetic engineering, all that stuff?
I suspect it is part of both. In fact, even the people who go to Europe and eat the pizza in Italy, and they say, come back and say, I have no problem with that, right? So it is, in that case, it's really how we produce wheat in our country versus we produce wheat there. It's much more organically produced wheat, right? The second part is, depending on if we are eating a lot of processed food, our gut microbes are actually no longer friendly to our environment. In that case, it is also, in addition to the food we eat, that's how it is grown, it is also our microbes have completely changed, are no longer able to digest the food they should have been able to do.
Is it that they can't digest the food, or is it that the makeup of my microbiome? So you talked about Akkermansia. There's God knows how many thousands of different species.
Billions.
So is it that I have the wrong makeup of the species, or is it that what I am feeding them is breaking them? Because, you've talked about this. I can put a microbe in the ocean to eat oil.
Yes.
So if there's a microbe to metabolize basically everything, is it really the problem with the actual bacteria? Or is it that I've gotten the bad bacteria to overproliferate in my gut?
You have to have the right set of, there is not like one single organism. There could be tens of thousands of different organisms that can actually metabolize that food, right? So one is part of having it. Other thing is the environment it finds itself in. So if there are lots and lots of bad stuff and it's crowding out the good stuff, when the food comes in, they may not even get a shot at it. Right? So in a sense, the things that could have been digested if there was a better balance is no longer. And I think in this environment, it is really interesting is not only we are feeding them, they are feeding each other, right? So it is one set of organism can take the food, actually poop out or metabolites that can be metabolized by some other organism, and then it produces something else. So in an environment, whether it is really good, it's actually not complicated. Look at Amazon forest, right? If you look at Amazon, any type of rainforest, every step you take has a completely different makeup, yet the whole place is lush and green. That means you can have a nice lush and green environment. They don't have to be identical. They can be very different.
Agree, but that's still, it feels like, given the second and third order consequences, that this gets complicated really fast. And given what I've been through with Lisa, I know how hard it has been, at least historically, to fix. Now maybe we're getting more
much
insight.
More closer. So what happened was,
what are we using to get closer? Is it AI? Is it AI chomping through massive data? What's the big breakthrough?
So the big breakthrough is actually analyzing the body as a whole. So let me just give you an example of what we did. 7 years ago, we simply analyzed your gut microbiome and trying to figure out
who's there,
biome, who is there and what they were doing, right? So remember, before us, everybody, including to date, every other microbiome company focuses on who's there. We changed that and say we're going to focus on not just who is there, but what they are actually producing. What are they expressing? What are they metabolizing, right? And then we say, oh my God, let's look at what they're doing. Is it good or bad? And can we use the food to say change their behavior, right? So that was first part. And then we realized and say, wait a sec, that's only a small picture. We don't know when these things get absorbed in the blood, how does the human host is reacting to it. So 2.5 years ago, we said, wait a sec, this is not going to give us everything we need. We're going to now analyze both your gut and a finger prick blood to know all of your inflammatory biomarkers. So what do we do when you get a finger prick blood? We're looking at all the human host gene expression, from your mitochondrial gene.
What are you inferring from that? The way that the body is responding? So walk me through, could I have good metabolites but a bad reaction?
So what we're measuring is what is happening in your immune system. So when we do a finger prick blood, the truth is at that point you have red blood cells and you have white blood cells, right? Red blood cells have no nucleus. You end up really analyzing the white blood cells. That means you're looking at all of the inflammatory markers, all the cytokines, right? So interleukin 1, interleukin.
And you're saying though that you could look at the metabolites and not be able to predict my reaction to those metabolites.
Not yet. So what we do is we're looking at you're looking at what your microbes are producing. Now we're looking at all the inflammatory markers and are looking at all the mitochondrial gene expression, right? So now we're looking at what mitochondria is producing, what your immune system is producing, right? What's in the blood. And then we're saying, wait a sec, this is what we see happening in the gut. This is what we see the human host responding to it. That's N of 1. And then we start to look at N of, say, 100,000. In our case, N of 500,000, right? Now we have lots of data to see every time we see this is what's happening. On N of 1, you cannot make that conclusion because they could be completely inconclusive.
If I'm understanding this right, it makes the following prediction that eventually you'll have looked at a data set large enough that you'll be able to know from the metabolite how they'll respond, or would you need to know my DNA and the metabolite?
No, so remember, this is not, we're looking at all of the immune system, how your immune system is reacting.
Yeah, but what I'm trying to figure out is, will immune systems react to a metabolite in a predictable fashion?
Yes.
Okay, so you could then eventually get a data set so big.
Exactly. Yeah, and that was the first, so this is what we did. 3 months ago, we said, wait a sec, we are still missing another part, as we talked about, the top of the tube. So we say, wait a sec, what's happening here is also impacting the human host. So why not analyze saliva to look at oral microbial activities and the human gene expression in your saliva? Look at both the gut microbial activity and the human gene expression from the epithelial cells shedding. And then look at the finger prick blood to understand all the human gene expression and take all this data together, and can you start making more sense out of it than just 1, 2, or 3 samples, right? And now that we have analyzed so many samples, we are able to in fact predict and give you the score where you stand. For example, when you do this test of full body intelligence, we analyze your saliva, your stool, and a finger prick blood. And then we give you your biological age.
The truth is, hitting your career goals is not easy. You have to be willing to go the extra mile to stand out and do hard things better than anybody else. But there are 10 steps I want to take you through that will 100x your efficiency so you can crush your goals and get back more time into your day. You'll not only get control of your time, you'll learn how to use that momentum to take on your next big goal. To help you do this, I've created a list of the 10 most impactful things that any high achiever needs to dominate. And you can download it for free by clicking the link in today's description. All right, my friend, back to today's episode. Before we add a confounding variable of biological age, I want to make sure that I'm understanding what you guys are looking for well. So we've got, there's an impossible amount of complexity here.
Yes.
So are there really billions of species of bacteria?
So there are billions of species, but in terms of the number of pathways or number of metabolites are much more finite.
Okay,
Remember,
so
there
the
could be
first
10,000
really
organisms.
usable thing is what metabolite is being kicked off. So I'm not worried so much about what bacteria you have, but I worry a lot about what metabolites are being produced.
That's right.
Okay, that's super helpful. All right, so now how many metabolites are we talking about? 10,000, 100,000?
Thousands.
Okay, but not tens of thousands.
Not tens of thousands.
Okay, so we've got thousands of metabolites that are being kicked off.
Yes.
Now those thousands of metabolites you've already answered yes to this, but I have a feeling that I'm not fully understanding what you're saying. Will those metabolites impact everybody's epigenetic expression the same way? Or will those metabolites be good or bad based on my current epigenetic expression?
When you say genetic versus epigenetic, I want to be very sure. So answer is yes, because epigenetics is changing your expression.
Yeah, that's why I want to stick to epigenetics. The actual expression in this moment.
So actual expression in this moment is what really matters. Your DNA, which is your original genes, don't matter as much, right? And the reason I don't say don't matter as much is, remember, the same alphabet can produce a lot of different things, right? In our body, every single part of our body, from hair to everything, is produced by the identical DNA, right? But we can make an eye out of it, we can make a nail out of it, we can make a hair out of it, right? So let's focus, what is epigenetics? So let me just define clearly. So your genes are there, which I think more you and I, even though we look so different, and you are 10 times as smarter than I am, with the same almost 99.8% same DNA. What really matters is in terms of tiny difference, but how epigenetically the things are being expressed, right? So epigenetic means, epi means over, genetics, right? So in a sense, in your genes, you could have methylation, which slows down the expression of that particular gene, or acetylation that actually increases the expression of that gene. Just by changing the expression of certain genes and under expression of certain genes, the same DNA can produce my hair, or it can become eyes, skin, lung, kidney, heart, whatever it is, right? Now, once it is expressed, it is called RNA. So you have DNA, then you have epigenetic, then you have RNA, right? So RNA tells you what is being expressed, and we are analyzing your RNA, specifically mRNA and the non-coding RNA. Right?
Can I ask you a question about RNA and DNA? So I was looking this up.
Yeah.
I don't understand RNA well yet. So is the process, I know I'm oversimplifying it, but if this is directionally correct, that'll really help me understand.
Yeah.
So is RNA, so you're reading the DNA,
yes,
and the reader is asking what is currently being expressed of these genes. And then it creates, because RNA looks exactly like DNA, but half. So like it's been, at least as it's shown on YouTube, it looks exactly like DNA, but cut in half. And
well, it's ACGU instead of ACGT. Yeah. So, right. And what is really happening is it control epigenetics.
But what is it?
Right.
Because it is made, it unzips the DNA.
Yes, so it looks at
and
the
you
codons.
Get a top and a bottom.
So you're looking at the codons, right? So you look
codons?
at codons. Like every three, there is a start, and there's a codon, right? So that literally tells you, take this stuff and express it, right? So depending on what control signals are there, which is methylation or acetylation, it says make more of these scripts or make less of these scripts, right?
Make more and less, or don't make?
Well, it's make more or less.
Really?
Yeah.
So it's still going to make some?
Yep.
Interesting.
Yeah, so it's not like methylation doesn't stop completely. If you're highly methylated, it'll completely stop it, right? But a slight methylation will still produce. It's not like yes, no. It's not just on, off.
I thought it was on, off.
No, it's actually more like a dimmer.
Okay,
right.
Very interesting.
And so having that dimmer is what allows you to have much more possibilities. Right. So that's the reason when you have methylation clock, it's not like, oh my God, is this on or off? The methylation clock allows you to see how much of it's on or how much of it's off, how much is dimmed and how much is not dimmed.
Okay, hold on.
Yeah.
So then, I hate derailing us from, because I still don't understand RNA.
Yeah.
But, so the Horvath clock,
yes,
which is checking methylation,
that's biological,
is checking the dimmer,
yes,
not on off.
Yes.
So are you looking for dimmer amount on certain genes?
So that's what they're doing.
All genes.
So we look at every single, so we're not even looking at the dimmer. We are looking at post dimmer, what is being expressed. Right, so we don't need to.
Well, I'm talking about, sorry, one step at a time.
Yeah.
Just the Horvath clock.
They are
because you mentioned your biological age.
Yeah, so I'm going to come there in a second here. So the way we measure biological age is very different.
Than
say, the methylation clock, the Horvath clock.
Really?
Right?
Oh, you guys have a totally different method.
Different. So here's how we do it, right? Because they're looking at one single source of truth, which is how much your human genes are methylated or not methylated, just human genes. And they're ignoring the 99% of the other stuff, which is our whole microbiome, right? In your mouth, in your gut, everywhere. They're completely ignoring it now, right? So what we do is very different. So when we say this, Tom, is your biological age, what we do is we say, look, We have now collected 600 trillion nucleotides. 600 trillion nucleotides from over.
I really wish I knew what a nucleotide was.
So RNA basically ACGT, base pairs.
Okay.
Right? So each base pair is a nucleotide, right? So once we have those base pairs, now we are saying is, okay, they're coming from these 500,000 people, 500,000 samples. Right? Now we say, okay, everyone we know what their biomarker looks like. So we create, let's assume some type of an algorithm that says, this is Tom's biomarker based on his saliva, blood, and stool. Mm-hmm. And then now we have created the biomarkers for every single age. So people who are 18 years old, 19 years old, 20 years old, 21. And now we have whole number of biomarkers for every single age.
So we snapshot of what all the nucleotides look like if you're 63, if you're 50,
that's right.
if you're 47,
exactly.
21.
Now you come along and we say, oh, we just analyzed
You
all
look
your
like
biomarkers.
this
You
snapshot.
look like just like this guy.
Wow.
Right.
That's really interesting if nucleotides actually matter for anything.
But point is this.
Convince me that they do, because I know nothing about
So
them.
basically think of them as RNA. So look at them saying, this is all the genes that are expressed in your body.
They're letter pairs.
But the letter pairs, but we're not looking just, so we're looking at
Letter pairs of the RNA?
RNA.
Okay, so we're back to you're going to have to help my slow mind
No.
grasp. Let me try to explain it and then tell me where my understanding breaks.
Sure.
You're going to be tempted just to go back to zero.
No.
Tell me where my understanding breaks.
Go for it.
To create RNA, you begin with a strand of DNA.
That's correct.
Then there is a thing, I don't know what that thing is.
Yes.
There's a thing that cuts it.
Yes.
Literally separates like a zipper.
Yep.
Top and bottom of DNA.
It's reading it actually. Just keep going.
Sorry, say it again.
It's reading it.
Reading it, but it's separating them, yes?
Well, the separation part happens.
It's called a fork.
Yeah, so it basically creates an RNA from a single strand.
Creates two RNAs.
Single strand, so that's what
Is it true?
Yes.
The top and the bottom.
Well, it reads both ways.
Because it's like, oh God, this is where at the edge of my understanding. It's like, what did they call it? Prime 5 and prime 3.
Yes, so they go both backwards. So they go back this way and this way.
Okay.
Yes.
Oh God, I only sort of understand this. But it is unzipping them.
Yes, it's unzipping.
So now I have the two
RNAs.
Pairs.
Yes, two pairs.
But they are separated.
Yes.
And now those are RNA.
And
yes?
No, so they are actually just a single-stranded DNA still.
Yep.
Right. The RNA gets created when it starts reading it, and you say, all right, this is one, this is one.
What's
so
this?
like you say, this is beginning and end.
This is one nucleotide?
One, not nucleotide, it would say one codon.
One codon.
And then you say, okay, and this basically starts saying, now this makes one protein or one metabolites, right? So literally you start producing amino acids. So remember, every one of them produces.
So every codon produces an amino
some
acid.
amino acids, right? So some number of codons will produce some.
So when when I am making the RNA, whatever I am, I am reading the DNA, which is methylated. So I know what's active and not active, dimmer switch.
Dimmer switch, how much is active.
And so do I remove things? Because I'm like, this codon is not active?
So this is so they only, when it's reading, now see, this is too deep a science. So I am now.
When I can imagine, if you don't understand, fine. I'm perfectly happy to get to the edge of your understanding.
This is where our chief science officer, Dr.
Would have to step in,
will step in and give me that thing. So from my understanding, and I'm not a scientist here, right, is to say, okay, these set of codons will produce this amino acids. And now we essentially are able, so the way we do is we look at all the genes that are.
So your clock says, this amino acid profile
or these
looks like this for this age, looks like this for this age.
So we don't look at the amino acid, we're looking at
But you're looking at the things that create the amino acids.
That's correct.
And since the only thing that matters is what they create, by proxy, at least, we are looking at the amino acids.
But what we're doing is really looking at the transcripts of everything. So we're looking at every transcript. We call them mRNA transcripts, right? So we're looking at all these.
But transcription is just turning DNA into
transcripts.
RNA.
Transcription is turning DNA into RNA, and what's turned is transcript.
The transcripts, are they what grab the amino acids?
They are the one who make the amino acids, yes.
They make the amino acids. Okay.
So this is where my understanding stops here. So these are the transcripts we are reading. Then we basically look at the network graph. If these transcripts are overexpressed, these transcripts are underexpressed, what metabolite is going to be produced based on these transcripts?
All right. What would Steve Horvath say why his method is better.
But
If you had to be super generous and steelman his argument.
no, so I would simply say is, look, there is no ground truth. So in a sense, when someone says this is better or worse or same or not, is what are we comparing against? So in a sense, like we all know what our chronological age is. Hopefully we all do, right? The biological age is a concept we all can determine, but no one can say this is the ground truth.
But the reason you think yours is better is it's more holistic.
It's more holistic and it has lots more people. So Howard clock is based on thousands of people. This is based on hundreds of thousands of people. And I'm not even suggesting that when it's better compared to what? Right? You can relatively, how do you know who is accurate? There is no ground truth to saying
who lives longer.
But
that'll ultimately be it. Look, it's going to take time, I get it.
But let's assume even you say live longer than what?
Somebody, like if the Horvath clock says, ooh, you're 20 years younger, take an actuarial table.
Yeah,
so you're supposed to live to 78,
but guess
you
what
live to
happened?
98.
Now you're looking at a statistical average. So it's again back to
You
the
gotta
same.
give me something. But if your Horvath clock tells me that I'm 20 years younger and then I live 20 years past the statistical age, call that pretty good.
No, but not really. I would say would be.
What are you using then? If you think my logic is flawed,
So here,
what do you use?
So if something, the logic of all of us are essentially saying is, hey, we know, are you relatively younger or older than your chronological?
Yeah, but I'm ultimately, all I care about is if the Horvath clock tells me to eat more onions and you tell me to eat less onions, then I need to know who's right.
Who's right? And the point I'm trying to make is that from our perspective, we look at the stuff and saying, okay, let's assume you were supposed to live 105.
Yeah.
Right? And let's assume you're 20 years younger and you die at 95.
Yep.
Have you lived your full life because your biological clock was wrong? Or you actually were supposed to only live to be 95? Right? So point is, just because you were 20 years younger but died at 95, but you could have lived to 105, that means biological clocks were
We're
wrong.
going to do a really complex problem, but let's solve it.
Yeah.
So what you're thinking through, just to say it in other words, is we don't know what the human life expectancy is in general, and forget the generalities.
Yeah.
What is your max potential? We don't know that.
Don't know that.
So the Horvath clock or any
clock,
biological clock
Yeah.
is simply giving you how much under your biological age you are, but I have no idea how long you're going to live.
And that's right. That is what I'm trying to say is, it's basically statistically we are saying you are similar to the person who is of this age, looking at very large population. And it doesn't mean
From a functional standpoint?
from functional perspective.
Okay.
That is what.
So you perform like somebody of this age, but who the hell knows how long you're going to live?
That's right.
Do you think that's going to be a totally different clock? So if Horvath and your clock, can we give your clock a name? Is it the Viome clock? What do we call it?
My biological clock.
All right. The Viome biological clock. If that is telling us performance,
Yes.
do you think there will be a totally different clock that's going to tell us average human expectancy times X? So 1.1, 1.2, like, because that's the clock I care about.
That's and the point you have is today different companies are looking at very different things. So for example, there is the inflammation clock, right? So the people say, hey, all it matters is how well your immune system is acting, because that's what determines how old you are.
So meaning, the clock seems like a weird choice of words there. Gauge?
Well, they call that inflammation.
Sure,
inflammation clock.
Can we agree that's a weird
It's
name?
a weird name, but it's basically score.
Is it a clock or is it a
score.
gauge?
It's a score.
Right.
Call it it's gauge score.
Okay.
Right. So your inflammation score in their mind is the only thing that matters, because that determines how long you're going to live. Because at the end of the day, if your body is highly
pretty true,
inflamed,
right?
it's, to some extent, inflammation, chronic inflammation is bad, right? No doubt about it. But that's not alone. Some people say the only thing that matters is your cognitive health. So if I can figure out your cognitive health score, that's your biological clock.
Yeah.
Some people say, well, it's your heart health. If I can figure out how well your heart is working, that's your biological clock. Some people say, well, what matters is how well you breathe. So I'm going to look at your lung clock and tell you, if that is what it is, that's how I'm going to tell you how old you're going to be.
And it probably will break out to those things. If your brain health isn't there, do you really care? If your heart gives out, do you care that you have better lung
And that's
capacity?
the reason the more set.
But this stuff directionally is very interesting. Yeah. Now,
and that's the reason, by the way, we look at least today, your saliva, your stool, your blood, and looking at those three samples rather than just one sample. trying to get as close to the holistic bio age as possible.
But let's abstract it back out. What's the thing that you, Naveen Jain, really care about? I care about function and duration.
Well, so I care about not just one thing. So what we do is we say, okay, you do this test, I'm going to give you your biological age. That's one signal, not the only signal. We give you your immune health score too. Now we're saying, hey, look at your immune health is doing good, but not as good. There's room to improve.
What do you guys look at on that?
Immune, looking at
overreaction, underreaction.
Well, no, actually looking at all of your cytokines, right? So remember, the immune system consists of all these interleukins, all these cytokines. So we're looking at the things that are anti-inflammatory. How are they being expressed? The things that are over-inflammatory, how are they being expressed? So the more inflammatory signal we are getting, that means higher the inflammation it is in your body, right? So we're looking at all of that stuff. Then we look at things like your heart health.
You guys are looking at inflammation already?
Yeah. So it's called immune health score.
In the blood?
In the blood.
What do you actually count?
We're talking all the interleukins and transcripts. Right?
How many of them there are? Is it just how many?
I just don't know.
That's interesting. I'd love to find out.
We're looking at tons of this. We know we get about 10,000 different types of scripts in the blood. All right. So we're looking at all those scripts. And then we are also...
When you say scripts, what do you mean?
Transcript, the RNAs.
Got
all right.
Yep.
And now we're looking at your, for example, cognitive health score. So that's separate score. It's called brain and cognitive health score.
You do that off the blood, or do you have people take a test?
Stool, blood, and saliva.
But those three tell you cognitive performance?
So we're looking at approximation as much as we get by looking at your GABA production, your serotonin production. So we're looking at all the things that we know today affect your cognitive performance, right? So it's a proxy for a cognitive health to say, hey, what is your vitamin D level? What's your GABA production? What's your serotonin production? And we see, or here are 10 other things that improve or decline your cognitive performance. We're looking at a proxy of those, right? Similarly, we're looking at the things on the heart health. What are the things that signal whether your heart health is good or bad? So we are looking at the things that would cause the heart health to be poor, such as your LDL production, right? So we're looking at all the different things that will produce the thing that will, in proxy, define your heart health, right? Similarly, we're looking at the things that will define your gut health. So we're now looking at the things that different parts of your body, and these are all different signals, including your biological age. But we're saying is, look, this is our approximation of where you are relative to all the people we have analyzed. So you really may be 63, for example, me, but I'm biologically fall as if I'm 50. That means my biomarkers match with other people who are 50. And that changes. So if I do a test a year from now, and if I'm not really taking care of my health, that may move up to 55.
How far do you think you can push that? Can you be 95 and perform like you're 50?
Time will tell. We have seen people who are 20, 25 years younger in their biological age and chronological age. Right?
Do you know who Brian Johnson is?
I know of him, yes.
He's coming back on the show, I think. So he claims, Scott, I don't want to put words in his mouth, that he's got the biggest gap between, the biggest reversal of age in the shortest amount of time. I think that's accurate. If you don't know what he measured himself against.
Well, my point is, again, in some sense, there is really no good, there's no ground truth. How do you measure
but you're proud of the fact that you're 63 and measure out at 50.
But that's based on our measures, right? And what I'm saying is that my biomarkers are similar to other people who are age 50, whatever that means.
But let's say that that's the gold standard.
If that was the gold standard, that means my physical performance and mental performance is similar to the people who are 50 years old. But doesn't mean I'm 50 years old. I'm still 63.
Yeah, what I'm trying to figure, that I get, but assuming that you kept those what I want to know very succinctly, do you think, and I know you're guessing, do you think that we can hold our biomarker static even as our physical age,
in fact, you
our
can
chronic
reduce.
age goes up?
I have seen it in the last 2.5, 3 years. We've been measuring the biological age. I've done last 6 tests. And then when I actually go off script eating the stuff that I shouldn't be eating, and I literally go on a vacation eating all kinds of junk, and when I do a test, my biological age moved up.
Whoa.
Now it doesn't.
How fast can you move it up and down?
I have not tested. I mean, 4 to 6 months even I test, and I've seen that quite a bit difference, like 5-7 year difference.
Whoa.
Yeah.
Is this like A1C where I can check like your last few months, you have on average been a 55-year-old?
Yes, so if I look at my biological age or by the way, so we show you the longitudinal data of as you test. So I can see here is my gut health, here's what happened, and as I'm doing this, I've done like 10 or 12 tests, where am I going? So is it getting better, is it getting worse? So every single thing you can start to measure for yourself, because you know the ground truth. Have you behaving yourself or you're not? We don't know that, right?
Okay, this is really interesting. So I check my glucose.
Yeah.
I wear, I don't know, maybe 4 months out
Yeah.
of the year, I wear a continuous glucose monitor. Amazing, I love doing it.
By the way, we built that into the system already as AI.
Tell me more.
So what we did is we actually put a CGM.
Are you partnered with somebody or you guys make your own?
So what we did, we don't have to partner anymore.
How do you get the glucose data?
So we basically built the AI model. So what we did is we took 1,100 people, put a continuous glucose monitor, fed them 70,000 different types of food, and then looked at the microbial activity and said, if we see this being produced by microbes, because we know that's going to change the glucose response, can we build a AI that will predict, which is what your continuous glucose monitor is showing, can we predict by looking at the gut microbial activity? And we published that paper with 87% accuracy.
Over what period of time? The glucose changes so rapidly.
It only changes from what food you eat. It's not unpredictable. So if let's
but my glucose will fluctuate by 70 points within an hour.
Oh, no, but for the same food?
Yes.
What do you mean 7? No.
Let's say I eat a bowl of ice cream. So it's going to spike hard, and then 2 hours later, it's back to normal.
So we're looking at a post-prandial, exactly what spikes to me. And now you eat ice cream again tomorrow.
Yeah.
Would it spike the same or would it be different?
Definitively not the same.
No, same if you had no other food, just that.
Correct.
That.
Come on.
So
you know better than that.
No. So what we do is actually the difference in the intrinsically is about 13% or so.
I don't know what you mean by that.
So basically,
here's what I'm saying. If I exercise my ass off and then eat ice cream, it'll be very different than if I don't exercise and I eat ice cream.
That's right.
There's a huge difference. If I don't sleep well. So if I sleep well, exercise, eat ice cream, very different than don't sleep well, don't exercise, eat ice cream.
Completely agree with you.
So how are you telling some in the metabolites of my...
Oh no, so what we're doing is we are saying is, hey, we took 1,100 people, right? And we say, keep doing what you're doing, so don't go out and change your behavior.
But people are messes.
No, but point is, and we bought the food for them. So we didn't say that, hey, go eat what you eat. You say, here is a food for you to eat, right? Don't change your habits. So don't go work out 4 hours today and then tomorrow you don't. Right. So we were trying to essentially normalize the stuff. Right.
I get it. So maybe I'm misunderstanding what you guys are trying to.
So basically, what we were able to do was now we can predict based on your gut microbial activity. And I'm going to come back to the oral side in a second here. Based on that, we were able to predict that when you eat carrot, you're going to have higher glucose response versus say for banana or for example
are you just
almonds.
Trying to come up with a like a glucose response per food?
Per food.
Okay.
Yes.
So not on any individual what you actually have that day.
For each individual.
Okay, so it's N of 1?
N of 1. So
so I have to run through this same battery of foods to get my own?
No. So what we do is now that we built the model, we can see based on now that so remember reverse. So we see this is what's happening in your gut microbial activity. If you were to eat carrot, we know what is going to do. Right? So we know this machine.
You're going to have to define what to do.
Okay. So
what metabolites I kick off?
What metabolites you kick off. So we know this is your code. So
but you don't know how my body is going to respond because there's so many variables.
So here is what we're saying. Those variables change what you metabolize, what your microbial activities are. So you know when you exercise a lot, your microbial activity changes.
Yep.
So we have now seen that when people exercise, their gut microbial activity changes. Right? So we know now based on the gut microbial activity, think of this, your code, that's a self-modifiable code. If we know what this code is going to do, we can say if this input happens, what the output will be.
Okay.
Right? So we know this is, we can analyze this. This is constant, so whether it's a carrot or almonds or...
So let me see if I understand this correctly. If I give you my microbial output,
yes,
you can tell me a banana is going to affect you this way.
That's right.
Very interesting.
Right.
Now, where do you guys see that going?
So what happens now, so now we are able to predict, to say, hey, don't eat banana, but it's okay for you to eat almonds. Or don't eat almonds, which are going to cause more spike than you normally people say almonds should not be high glycemic response. We can say, for you, Tom, almonds are really high glucose response. Don't eat almonds, but you can eat banana.
Okay, so having listened to as many interviews with you as I have, I know that this stuff changes very rapidly, and that one day you're predicting that the toilet will just give you this information. So you will make a deposit, and then the toilet's going to be like, hey, eat almonds today after 3 p.m., but make sure that you do your normal 75 push-ups.
But we don't really, so in a sense, as long as we know what they are expressing, because all these things you do, whether it's exercise or sleep, all of those are changing what you're expressing. So the reason you feel bad or feel good is something is being expressed differently.
How rapidly does it change? Glucose is by the minute almost.
So glucose is not by the minute. If you, no. So let's assume
You don't agree with that?
No. So I'm just not for the same food if you don't change anything else, right?
Understood.
So my point is, So let's assume you don't eat today, right now. If you say, okay, I eat the same oatmeal 4 hours later, and I have not done any workout, or I normally do 30 minutes of workout after I do
all
oatmeal.
variables held steady, including the metabolite production.
Metabolite production we can measure. So you don't need, so we say, hey, you work out, we know what they are doing, because that's the code we can analyze. Right? Now, once we know what they're going to do, we say, if this input you give us, we can tell you what the output is going to be. Right? And that is our glycemic response model. What we did very recently is we said, hey, how much of information can we just get from one input like saliva? Because we were thinking that this requires you to do 3 things: a spit in a tube, touch of a stool, and a finger prick of your blood. And we're thinking, can we get 60-70% of the information just with your saliva? So we said, okay, now that we have 100,000 people that have given us all 3 samples, right? And now we are able to actually understand what is the ground truth based on all 3 things. Can we now build the AI model to predict what is going to happen for the glucose response just from saliva, even though there is no research ever done? So we say, we know from stool to glucose response. Can we build a model from saliva to stool in proxy for this glucose response? And we did that.
Amazing.
Right.
How close is that? How accurate?
84%.
Wow, just from my saliva. So from my saliva, would you be able to tell me, hey, today, based on your saliva, bananas are going to have this response?
Yeah.
Wow.
Yeah. And
84%?
84%.
It's amazing.
Yes.
What do you think, what's the error on? Is it like a wild miss, or is it like...
As you mentioned, each person, there is a variant in each person, even if you forget the other people. So just you alone, there is going to be 15-16% variation just inside you.
That's it?
Yes. For the same food with all the variable being the same.
So is your prediction, and I get that this is a complete guess, I just want to make sure I'm tracking your logic. Is your prediction that at 16, I eat this thing and it has this response, regardless of what I'm exercising, doing, all of that.
You're 16 years old.
At 47 years old, I eat the same thing. I'm going to be within 16-ish%.
No. Because your activities are completely changed now. So if you remember, as you are aging, and your whole lifestyle, the place you go to, the people you meet, how much of time you're spending in the nature, how much of the things, other things, environmental
things. So you
things.
do need the real-time response to get me within 84%.
That's right. That means you need to be able to do a test so we can analyze what your microbial activities are, which are different from when you were 16 and versus you're 47.
Yeah, so maybe I asked the question poorly. What that says to me is that the 84% represents the difference between what's actually happening and what you can guess from the saliva.
That's correct.
So, okay, so you're making these inferences, but it's a
reasonably good approximation.
16%-ish here that we just have no idea, we can't tell.
And we don't know why it's causing that, because we believe that, at least in our belief, the human body itself has that variability for other factors that we don't know what they are yet.
Still incredibly interesting. How do you think that with a big enough data set that you can crush that gap down?
It will continue to get closer and closer. To get to 100%, we need to be able to write the human body. That means we know exactly what's happening, and we can create a human body because we know everything that happens in the human body. And when we get to that point, we start to play God, right?
Yeah, well, that's interesting. Play God for a second. So what are the gaps? What would we need to understand?
The truth, Tom, is we don't know what we don't know yet. We don't know. It's not like we're saying, hey, we know these things, we just need to do them now. We don't even know what we don't know. It is human body is so complex. Every single day, we're learning something new. And we say, wow, we didn't know that. Right? For example, NAD. How many times people have said, you want to live long, take NAD or NR or NMN. Research came out last month that says NAD and NR actually causes onset and a progression of cancer. Metastasize the cancer.
Only in some people or in everyone?
In some people, right? And now we need to understand what is it that's going on that's causing that. We don't know that.
This is why I'm so paranoid about supplements.
Right. So honest to God, that's the reason I tell people don't put anything in your body unless you have analyzed it, right? So what we do is slightly different. Again, I'm not suggesting that we got 100% of it right. So what we do is we say, hey, having analyzed your saliva, having analyzed your blood, having analyzed your stool, we don't think you should be taking vitamin B3 because your uric acid production is too high, and we know this niacin vitamin B3 is going to create more uric acid and it's going to end up turning into gold. Or your bile acid production is very high right now. If you take curcumin, which everyone tells you is really healthy, is going to actually increase more bile acid, convert into more bile salt, is going to cause more inflammation, not less inflammation. But you do need, we see this pathway is not very active for you. You do need about 22 milligram of CoQ10. You need 70 milligram of lycopene. You need about 50 milligram of the blueberry extract, right? So we literally go through all the food extract, vitamins, minerals, herbs, digestive enzymes, peptides, probiotics, and prebiotics. And literally say you need 22 milligram of this, 18 milligram of this, 79 milligram of that. And we literally say, this is for Tom. We built the whole robotic machine now that literally say this compound, this is being produced for Tom. Here are the things you need. Go to bin number 3, get 22 milligram. Go to bin number 22, get 18 milligram. Go to bin number 27, get 95 milligram. Create the powder, shake it up, put them in a capsule, and send them off to you. And that's literally what it is. Every single month, we make it, custom make it for you, right? Same thing here.
Based on my updated test.
Based on your updated test, right? Now, we test every, 6 months, 4 to 6 months, it gets updated as things are changing. Our goal...
What gets updated?
Your supplements, what you need or what you don't need, right? So
do you think they stay good for 4 to 6 months?
Well...
What would be ideal? Would I test every day?
3 to 4 months. Body doesn't adapt that quickly. So 3 to 4 months will be absolute. I mean, if you want to be an absolute optimal, 3 to 4 months. But 6 months is good. I mean, it's not like they expire somehow, that your body is completely different now, you expire, right?
Interesting. That's the one thing that, and I don't know enough, so I could be totally wrong, but it feels like the body changes a lot faster. Like if you track the microbiome, you can see from day to day that there's pretty big swings.
So here is what we saw. We actually have a published peer-reviewed paper. We took people to say, again, this is a caveat. We told them not to change the way you live.
Sure.
And we say, keep eating whatever you normally would be eating. And every month, just the way what you have been doing. And we analyze their poop every single day for 30 days. And then we actually put them things together and we say, we know exactly which poop come from who. That means it didn't change significantly in terms of what
if you tell people not to change, I don't know how much that affects it, but have you looked at what the relationship is for people 4 to 6 months on? Like what percentage, is the average person 96% the same every 6 months, or is there massive variation?
So if you change, so let's assume we say, hey, here are the foods that are really bad for you, don't eat them. And here are the foods that are superfoods for you, eat these. And we tell you why. So we say, here are the foods you really need to eat and here is why. Don't eat these foods and here is why for you, not for someone else, for you, what's happening. If you follow all that.
What is up, my friend? Tom Bilyeu here, and I have a big question to ask you. How would you rate your level of personal discipline on a scale of 1 to 10? If your answer is anything less than a 10, I've got something cool for you. And let me tell you right now, discipline, by its very nature, means compelling yourself to do difficult things that are stressful, boring, which is what kills most people, or possibly scary or even painful. Now, here is the thing. Achieving huge goals and stretching to reach your potential requires you to do those challenging, stressful things and to stick with them even when it gets boring, and it will get boring. Building your levels of personal discipline is not easy, but let me tell you, it pays off. In fact, I will tell you, you're never going to achieve anything meaningful unless you develop discipline. All right, I've just released a class from Impact Theory University called How to Build Ironclad Discipline that teaches you the process of building yourself up in this area so that you can push yourself to do the hard things that greatness is going to require of you. All right, click the link on the screen, register for this class right now, and let's get to work. I will see you inside this workshop from Impact Theory University. Until then, my friends, be legendary. Peace out.
What happens is now suddenly the input is changing. This activity changes. So it doesn't need your microbiome is changing, your microbial functions are changing because now you're giving them a different things to metabolize, right? So that change, so your functional activity is changing. And we have seen the people who change, their microbial activity change quite a bit. If you don't change anything, so let's assume we tell you to do this and take these supplements, this probiotic, you say, not going to do it. And you go back and analyze 6 months later. And if you more or less stayed the same, probably your activities will be more or less the same. If you started working out, they probably will be different. If you start spending more time in nature, it will be different. So if you start, yeah, of course. Because remember, every time you are in nature, you are inhaling, you're constantly being bombarded by the microbiome, right? When you go past the cow dung, you smell bad. What is that? You're suddenly inhaling all that stuff, right? So that's how your aromatic sensor says, oh, well, that smells like shit.
Will that make its way to the actual gut?
Well, it starts to make it to your body, right? And then when you're smelling through your mouth, it's starting to go, the microbes are constant. By the way, when you and I are probably breathing billions of microbes every time just when we're breathing in and out.
That's so crazy.
Right? So if you could have a microscope here, you'll be seeing.
Yeah, I don't think I want that. Yeah.
You get my point. But every food you eat is full of microbes, right? Whether you eat animal food or you eat the plant food, you literally are essentially getting a whole bunch of microbes.
What's your take on meat eating versus non-meat eating plants?
So again, when people have this fundamental idea that if you are vegan or plant food, you are healthy, without realizing almost all the poison actually does come from plant. So just because you eat plant food doesn't mean you're actually eating healthy.
Poison that humans have put on it, or the actual plant protective
plant poison,
mechanisms?
I mean, look at poison ivy, right? I mean, a whole bunch of poison actually comes, a lot of the drugs come from plants, right? So the point is just because you think it's plant doesn't mean it's necessarily good for you. And again, idea is.
But if I were going to eat the optimal plants versus the optimal meats.
Yeah, so I would say it depends on, again, so here's what happens. Meat, let's start with red meat because everyone thinks it's bad. And you and I probably know lots of people who ate red meat and potatoes and lived to be 100 years old and lived healthy, right? What is it? So the red meat contains choline and carnitine. When it goes into your gut, your microbes change that into something called TMA, trimethylamine. And that gets absorbed into the blood and your liver turns them into TMAO, trimethylamine oxide, which is what causes the heart disease or plaque in the arteries. So if your TMA score is low, you can eat red meat because it's not going to impact much. Versus if your TMA is high, if you eat more red meat, you're going to produce a lot of TMA, which is going to produce more trimethylamine oxide. That's going to cause more heart disease for you.
Is that at an epigenetic level, or is there a genetic marker that you can look for?
So this is microbial marker. Remember, so this is what microbes produce that take the meat and produce TMA.
Interesting. So depending on how I have cultivated my microbiome, I either can or can't eat meat.
Or can eat lot or little.
Interesting. So do we know what the magic cocktail, like I like red meat the most.
Yeah.
So what cocktail of microbiota do I need to be able to eat all the red meat I want?
So we can actually tell you that if we were to analyze today, we can tell you what your TMA production looks like.
Yeah, but you should also be able to tell me what I can eat to migrate my microbiome to one that's friendly.
Yeah, so that is actually a really, really good question. Can you actually precisely adjust to say, I want to eat this food? Can you make my microbiome compatible with this food?
Yes, please.
So theoretically, the answer is yes. Practically, we don't know yet. Right? But theoretically, there is no doubt.
What's going to be the solve for that? Is it AI?
It is AI and the data and it's more than nature of this ecosystem. It is so complex that when we change one thing, we believe that's the only thing we are changing.
Yeah, but can't you really just look at the data on this one? This feels like if I give you a large enough data set, and I think you're over the next 5 years, I think people are going to keep pouring into this. So let's say you have 500,000 now. Let's say that you have 500 million in 5 years.
It absolutely gets solved.
So if we have 500 million data points, could we not start going, okay, people with this snapshot of their microbiome, they have less heart disease, whatever?
Yep, we absolutely can. When you have that large a data set, you can solve very, very complex problem, right? And today we are saying we're getting closer and closer, but we are nowhere near understanding the human body complexity, and it just requires a lot more data.
Yeah, but couldn't we get away with just correlation on this?
You can, except that the problem is, if you have, let's assume, 10,000 species capable of producing hundreds of millions of types of potential interaction. Remember, if every microbe has, say, 1,000 genes it can express, at any point it's only expressing 100 of them. Right? So,
do you think that there's a microbiome type? Like, are we going to, with enough data, will we get a snapshot that says there's 52 types of microbiome? There's of course, the nitty gritty is wildly different. But for instance, because I play in the world of NFTs, you create these collections of 10,000. But the 10,000, they still, it's pretty easy to tell one collection from another. So wouldn't it be, I'm going to hypothesize that with enough data, what we're going to realize is there's some finite number that is not crazy. Let's call it 52, because I think that's probably going to be relatively close. And you say, okay, the people that live to 120, they all have this pattern, not just of the microbiome, but the 3 snapshots or whatever. They all look like this pattern. And if you eat roughly these 416 things and exercise in this amount or whatever, then you're going to get that pattern. And now we can check it and see, your markers all line up with the people who live to 120.
So what we see is really interesting is even the people who are healthy, right? Just like we talked the example of the rainforest, right? So you can have 2 people who are healthy, can have completely different set of organism because they're all producing similar types of things that keep us healthy. So it's not...
When you say organisms, what do you mean? Because metabolites are all we care about.
So see, when you say these microbiome is not metabolites. Microbiome is the organisms, right?
But do we care about the organisms?
We don't. That's my point. So when you mention, you say, can we come up with a set of these microbiome? And I'm saying microbiome functions. Yes. So can we come up with the microbiome functions that they are performing? And can we come up with some subset of them, whether it's 52 or 500, some smaller numbers, finite numbers, and we see if the people who live to be healthy 95. By the way, there is a study done there. So they took the people who were in 90s and they were healthy versus people who were 90s and not healthy. What they found was the people who were in 90s and healthy, their gut microbial activities are very similar to the people who were 30 or 40. Right? So,
wow.
Yes. So that means they maintain the microbial activity to be healthy, and that's why they tend to live longer. And that's just only one function they analyze. Now, obviously, they didn't, in this particular study, they didn't look at the stuff and say, what is their immune system doing? What is their oral microbe doing, right? But in this thing, they did look at the gut microbiome and showed the people who live healthy to be in 90s had a microbiome to be much younger person, the activities.
Okay, so there's a lot that we can learn from these snapshots. Yes. Talk to me about what you guys are learning about through, I assume, data sets, AI, that you're able to start making predictions around cancer.
Yes.
I know you guys are going to be releasing or have released, being able to spit into the tube. What's the relationship? At this point, is it just a data relationship? We know that people with this oral microbiome tend to have this kind of cancer, or is there actually something that's correlated?
So here is what we did, and then I can explain what happened. Right? So this is what we did. We said, hey, people who have stage 1 cancer in the mouth or in their throat, their human genes are expressed like this, and microbial genes are expressed like this. And then we took enough data to say, hey, I think we can now predict if you have a cancer, not potential to have a cancer. You actually have a stage 1 cancer, stage 2 cancer, stage 3 cancer. And then we say, okay, if this is the model, can we look at completely unseen samples, run this model against them? So we say, all right, we're going to take 120 samples. Don't tell us which one of these samples have cancer or which ones don't. We're going to run our AI model, and we're going to say, here are the samples we found to have cancer, or stage 1 cancer, stage 2 cancer, stage 3 cancer, and we found these samples not to have a cancer. And when we did that, what we showed was we were able to be specificity of 95%.
God damn.
Right? We can say this were right. So that means 95 out of 100, we say these people have a cancer. And 90% sensitivity when we say these people did not, there was a 10% chance they could have had it. Right? So we were able to now take that data, went to FDA. FDA gave us a breakthrough device designation.
How long did that take you guys?
So that's take about a year. And breakthrough device designation has 2 meanings under the FDA. Nothing like this exists. That's why it's a breakthrough. If some test like this exists, they would say, just go through the regular approval.
Right.
And this thing, what you're doing, would save people's lives. Right. So they say this thing is a complete breakthrough. So today,
you can market this as cancer detection.
We do it right now. So you can go to our website. It's called Cancer Detect.
Is this your biggest line of business?
This is the recently launched test, which we think could be that's just the beginning, by the way. So we started with the thing you spit in a tube.
Are you marketing this?
Yes. Right.
So what's the response? Like, this is so insane. I'm like, am I understanding this correctly?
No.
So people that have cancer, you can detect 95% accuracy. People that don't have cancer, you're 90% accurate.
Cancer in the mouth
and throat.
And the throat. That's all so far. Just want to be very clear.
That's amazing.
Right. But we are now going down the tube. We are now looking at the esophageal cancer, stomach cancer, colorectal cancer, pancreatic cancer, lung cancer, liver cancer. And then we're looking at other diseases, Tom. IBD. Today,
IBD,
which is intestinal bowel disease, inflammatory bowel disease, inflammatory bowel disease. So people have Crohn or colitis. People have them and they pain, they don't know what is going on. We are able to now build a model that we're going to be launching in the next 3 to 4 months to be able to predict with almost 97, 98% efficiency that you have a Crohn or colitis or you don't have IBD.
Wow.
Right. And
where are you guys at on the, can you speak to where you're at on the cancer, on those? I know you're not approved yet, but.
So those two, this cancer in the mouth and throat is already launched as a laboratory developed test.
Right. Colorectal seems the most
colorectal
important.
cancer to me is coming. We have in fact the data being collected. What is more interesting is not colorectal cancer actually. To me, what will be the real game changer would be colon polyps. Because colon polyps
just that you have them
8 to 10 years before they become cancerous. Right. So if we can predict you have colon polyps, then we can say go to the colon, get the colonoscopy and get them removed because they'll never have a cancer then. So to us, the breakthrough is going to be to detect colon polyps. And we literally are collecting all the data. So when you go to colonoscopy, we get your samples, saliva, blood, stool, and then we get the physician report. Did you have colon polyps? Do you have a colon cancer? What is it?
Are you spending most of your time on the medical side of this or the AI side?
So remember, both.
You personally.
So I spend most of my time trying to find these breakthroughs. But remember, none of that can happen until you have this massive amount of data. So what happens is our business, which is our wellness business, allows you to stay healthy. In turn, we get all of this data. People who have depression, what their biomarkers look like. People who have anxiety, what does their biomarker look like?
Yeah, so what I'm trying to figure out from your, when you, as I'm listening to you say this, I'm like, please stop focusing on the medical stuff. Just collect as much data as you can. By your team focusing on the medical stuff. But figuring out the AI component of this feels like the huge breakthrough. And this is crazy that you can detect cancer in saliva.
Yes. And in fact, not only that, we are able to see that how the human gene expression changing when microbe expressions are changing, because that's what causes the cancer. So in fact, what is really interesting, Tom, and I'm not sure we talked about last time or not, they are able to now look at all the solid tumors, and every single tumor they looked at, there is a unique microbiome inside the tumor of every cancer.
That you think will show up in the blood?
That will show up in the blood. Right. So imagine, what is that? The interesting question is, what is that microbiome doing inside the tumor? Right? And one of the interesting things is, at least the research is showing, that these tumors are displaying these microbial peptides on top of the surface of the tumor. And it occurs to me, why would an organism like cancer, who wants to survive, want to display to the immune system, come and kill me, unless these microbial peptides are declaring themselves as self, protecting the tumor against the immune system and saying, hey, we're all good here, we're all friends here, don't worry about us.
So wait, how does that work? Why did you first think that it would be a signal to come kill me?
Because anytime there is a foreign agent on anything, something foreign, immune system wants to attack that foreign thing.
Yep.
So why would a tumor display a microbe that's supposed to be foreign, putting up on the surface, inviting the immune system to attack it, unless they believe that substance is telling the immune system that we are part of you, part of self.
So do you think they're misunderstanding that?
Well, microbes are essentially some of these microbes are part of our self. That's the reason the immune system doesn't attack them. Right? And some of these microbes have now learned, which is autoimmune disease. When your microbes are starting to produce the amino acid that may match with your, say, for example, your protein in your joint, guess what happens? Immune system thinks it's attacking the microbial metabolite, ends up attacking your own joint, and that's an autoimmune disease now. Right? Because there is no reason for immune system to attack our own body.
Yeah, I'm missing something on the cancer. Take us back to the 101. So cancer displays things on the surface of the cell.
That's what we're seeing. So we don't know the mechanism. I'm just saying that is my hypothesis.
But what does it put on the cell?
So it is producing the stuff from the microbiome that microbiome is producing, or the cell of the microbiome that it is on the surface of the tumor. That's what we see right now.
And your question is, okay, cancer, you're putting something on the surface of your cell that the immune system is going to recognize as foreign, and it's going to come and
it's
attack
not
you.
recognizing as foreign, it's recognizing as self, so it's not attacking the tumor.
Is that your hypothesis?
That's
or
my
what
hypothesis.
You know?
That's my hypothesis. And that's the reason the immune system is not killing the tumor. And so reason must be that it got to be something that
there's something about displaying the microbiome on the surface of the cell,
or some
that says
other,
all is well.
Yeah, all is well. Otherwise, immune system should be killing that cancer.
Okay, so let me restate your hypothesis to make sure I understand it correctly.
Yeah.
The immune system is very used to seeing microbes.
Yeah.
Because we've co-evolved from mitochondria to what's in your mouth, what's in your gut, all of that. But in the blood, it's a different story. Anyway, let me finish your hypothesis. So the body is very used to seeing that. The cancer cell is putting it on the surface of its cells. You think it's doing that as a way to say, hey, we're just another microbe, all is well. But the body also kills the shit out of microbes.
If the particular microbe pathogens, it makes...
Yeah, so what is it about the microbiome on a cancer cell that looks like...
know. So there is a reason why our immune system is not attacking our microbes in our gut. What is it that it's doing? Because at least our understanding of the way immune system works is when the baby is born, the microbiome in the gut starts to actually create, I forget the gland, what is the gland that produces the T cells and B cells? It starts to actually translocate to the things. So it says, hey, now we understand who you are, and we're now going to produce the antibodies against you so that macrophages can attack you. Right? So it starts to say, okay, we understand this is no different than our human tissue. Right? And once it gets trained, then that's the reason, even though 70% of our immune system is along our gut lining, it's not attacking our gut constantly. Right? And we don't know a lot of this mechanism. So I wish I could tell you, hey, we know exactly what is causing cancer. We know exactly how to solve it. The answer is we don't. I'm just telling you what is our current understanding, what is my hypothesis. Again, hypothesis doesn't mean the fact.
Sure.
It needs to be validated. So scientifically, all that means is we believe something that may scientifically turn out to be right or wrong. And then if it is right, then it becomes a theory. If it is wrong, it goes out the window, right? So currently the hypothesis is not even a theory.
Yeah. Okay, very interesting. So,
by the way, that's why it's called impact theory or, health theory. The theory means when you start to make a hypothesis and then you prove it that hypothesis is true, then it becomes a theory.
that it seems true so far.
Yes.
How about that?
That's true so far.
Exactly.
Yes.
Okay, so going back to cancer, I know your dad died of cancer, and that's a big reason why you started doing this. So your dad died of pancreatic cancer.
Correct.
You were just saying that you think that you'll be able to detect pancreatic cancer? How?
Oh, so it's actually very interesting. The research clearly shows, at least there was a NYU professor who showed that pancreatic cancer is caused by a gut microbiome going through the bile duct, translocating into pancreas and actually making the tumor, or at least helping the tumor grow. And this particular professor injected the antibiotics directly into the tumor in the mice. And that killed the microbes, and immune system killed the cancer. So something happens magically when they put the antibiotics. What did it do other than killing the bacteria that caused the immune system to kill the tumor? That means that's where the hypothesis comes. Were these microbes protecting the tumor because the immune system wasn't attacking until they killed the microbes?
I think we have to talk about phages now.
Yeah.
So
Yes.
describe to people what phages are, because there's a very interesting relationship between phages and bacteria.
Absolutely correct. So let's just define the microbiome for a second, then I'm going to come back to the phages. So microbiome, most people think is just about bacteria. Microbiome is, micro means small, biome means life, the organism, right? So the life, small life. They can be bacteria, they can be viruses, and viruses can be, by the way, normal viruses or RNA viruses, which are basically don't have any DNA. They're just RNA viruses. So they can't be detected any other way unless you analyze RNA. Right? And then there are viruses that are called phages. And then there are obviously the fungi, and the part of the fungi is mold, right? So that's basically.
Are viruses and phages synonyms? Same thing?
So phages are a type of viruses that only infect bacteria.
Okay.
Right? So the phages are in nature, there are 10 times more phages than bacteria. Right? And every spoon of soil you take, there are trillions of these organisms. Right?
These deadly viruses that kill like 95% of all life on Earth,
Right.
which I didn't realize until I started
So
researching
these
this.
phages actually only infect bacteria and change the function of the bacteria.
So they can only kill bacteria, which is
Not
why they don't kill humans.
Kill. See, that's, I think.
They don't kill bacteria?
No, they infect the bacteria and change the function. Remember, now they've injected their genetics inside the bacteria, right? And that.
But doesn't the bacteria just replicate the phages?
So it replicates.
And then ultimately it bursts the
So
bacteria.
point is, it's not just creating phages, it's creating the bacterial functions is changing, and it becomes symbiosis sometimes. So we also know, at least from what we have seen, the phages change the behavior of the bacteria in terms of the functions they provide. That's all I can tell you with certainty.
Right. Okay. So phage. So here was why I was bringing this up now.
Yeah.
One of the things that I came across, and again, I'm at the very early stages of really understanding phages and bacteria, but one of the things that I came across was that you have this really interesting inverse relationship between antibiotics and phages. So because phages and bacteria are in this constant evolutionary arms race where the bacteria is evolving to avoid death by phage, phages are evolving to make sure that they can take over the bacteria. In this arms race, the phage can only work against the bacteria can only battle off the phage or the antibiotics, but not both. So it has to choose an evolutionary path of protect myself from the phage or protect myself from the antibiotics. If it protects itself from the phage, it will die. The antibiotics will now be able to kill it. Because I was researching superbugs. So by like 2050 or something, superbugs may be the leading cause of death, which is crazy. That's only 30 years from now. So less. So if that ends up being true, we have to come up with this countermeasure. The countermeasure is phages.
So let me just one more thing, concept I think that might become very clear. So the way the bacteria deals with phages, it created a mechanism called CRISPR. And I'm assuming, so the CRISPR that we use to modify our DNA actually came from bacteria. So what bacteria does is, once it sees a particular type of a phage, it remembers the sequence of that phage.
It's genetic code. I know some of them don't technically have genes, but like that sequence of ATCG, or would it be
ACGU or ACGT, depending on what it's, an RNA virus or a normal virus, right? Phage, I don't know if the phage can actually be the RNA phage or not. I don't know that. But so let's assume they're DNA phages for the time being. When it comes and infects the bacteria remembers the sequence of ACGT, and then next time it sees, it cuts it. So that no longer can replicate anymore, right? So the replication of the virus phages completely stops. We learned that mechanism of how to recognize the sequence and cut it. And this is what we use now. All of the companies like a CRISPR and stuff that you may have heard is to modify the human DNA. They're saying, can we find a particular mutation in the human DNA that causes these genetic diseases?
Still so insane to me.
These causes the genetic diseases of this sequence, and tell our DNA, hey, this is the sequence to cut, and use the same mechanism that finds the sequence in the bacteria. It's called CRISPR-Cas9, and Cas9 is the guide that tells you where to cut, right? And the CRISPR does the cutting. Right. So anyway, the point I want to make is that we learned from bacteria a mechanism that it uses to save itself from phages. Antibiotics are primarily designed to attack, not primarily, they're only designed to attack bacteria and not viruses. So antibiotics, the problem is, even when we have a viral things, whether it's a flu or cold, we take antibiotics. It can't do anything with the virus. It's designed to kill bacteria. And the more we take antibiotics, it's like throwing a nuclear bomb inside. It kills everything, good, bad, ugly, everything is gone. And now your whole gut microbiome is gone, your oral microbiome is gone, and you're toasted, right? And now you have to restart again, right? So now the idea is, can we actually detect that when we are taking antibiotics, don't take it, overuse it. When we do overuse it, what happens is these bacteria start to know how to defend itself against this particular antibiotics. So we have to keep evolving new types of antibiotics. And the problem that's happening is the companies are no longer developing a new antibiotics because the shelf life is so small, they can't make enough money. So they stop producing new antibiotics.
Because the bacteria find a way around it so fast?
But bacteria eventually find a way around it, then antibiotics doesn't work, and nobody wants to spend multi-billion-dollar developing a new antibiotics that may have a short shelf life. Right? So they're saying is, wait a sec, it's no reason to develop a whole bunch of new types of antibiotics. And if we keep taking the current antibiotics, our bacteria evolve to actually defend or not be attacked by these antibiotics. And that's what creates these superbugs.
What do you think about that? What's the solution?
Solution is very simple. Cut down the use of antibiotics, cut down the use of over sanitization. So constantly using the Purell on our hand. And I saw someone who is really paranoid, does it all the time. Guess what? It's evolving these bugs to actually save itself. Learn how to not get killed. Right. So the more you do sanitization, the worse over a long time it gets.
But is that really, so that seems like a completely ineffective solution. It's one of those, it would work if people would do it, but people aren't going to do it, especially not as we come out of COVID.
And by the way, everything we do to kill the gut microbiome is problematic, right? So food that we are eating is, pesticides. What is pesticide supposed to do? Kill these organisms.
Yeah.
When we eat the food with pesticide, what does it do? Kill your microbiome, right? So, and now what happens is now your superbugs are being evolved to survive against that, attack.
So does this seem like, are you really pessimistic about the avoidance of superbugs?
No, what I am pessimistic is that would humans actually start to take care of themselves before we start to lose our human species, right? So in a sense, would we start to grow more organic food where we are able to use the microbiome of the soil itself? Because remember, microbiome wants to survive. It will fight the pathogens. It will fight the bad stuff if you really start to create the diversity in the soil. So growing multiple different types of food, putting in more and more stuff which is organic. So cow dung, all that stuff. What is cow dung? Basically full of microbes, right? And that's literally how we used to grow food that made the soil rich. It made the microbiome fought off all the pathogens, and we actually had a good, tasty food actually, and really good organic food. So I think we all have to go back to how we grow food and, start to grow the way it was supposed to grow. And I'm not against hey, don't evolve. I'm not one of the Unabomber that, all innovation is bad. Innovation is good, but they're not all innovation is good.
So how do we deal with bad innovation? And let's put it in the context of AI. So literally 2022 is the year, if people want to plant a flag, it's the year that it went from deceptive to disruptive, where now I'm watching debates on Twitter where people are saying
ChatGPT is a good example.
Yeah, like literally abolish this. I saw a guy today, it made me laugh, where he's an attorney and somebody put a video of GPT writing a contract. Somebody just put a prompt. And he was like, you contact Congress, make this illegal. I thought he was kidding, but he's actually being serious. So how do we deal with
First
this
of all,
level of
really good
disruption?
introduction. I think one of your person here, just before I came on, he typed in, give me an intro for Naveen Jain. And it literally typed the intro that you could read, right? It's good, but the problem is very, very early stage. In fact, if you ask it a question it doesn't know the answer to, it makes up the answer based on the fact, just like a brain does, right? It says, I know this, and now let me make up this answer, right? It doesn't know to say, Tom, I think you're going beyond my knowledge right now. I don't know the answer to this. It actually makes up the answer. But someday, could we create, general purpose AI or AGI, right? That is going to be very, very difficult, at least for the next 5 to 10 years. So we are nowhere.
I would say forget AGI for a second, and just go. So literally, I think this week, Elon Musk released fully autonomous self-driving cars. And he says 95% of people don't even realize we've released this yet.
And by the
so
way,
it
is not. Just remember, man, Elon Musk has what he says and the truth sometimes may diverge a bit, right? So a fully automatic car is someone you can actually sit on a back seat and let the car drive itself in all situations. And we all know what has happened, right? I mean, will it improve over time? Yes. Today it gets confused between a pedestrian or for example, or somebody could have a cutout of a person. It doesn't know the difference. You and I can look at the stuff and say that's a cutout. That car may not know the difference, right? So the point is there are a lot of real world situations where You and I, until we have all the cars that are following the same rules, if we have humans and this car interacting, you and I, when we're on a 4-stop sign, we try to move a little bit and see if other person is really, and he said, all right, you go ahead, right? If you have a human and this car, it doesn't know the dance to play. AI can play the dance. If all cars suddenly were using exactly the same software, they can negotiate against each other in that particular situation. But it can't negotiate against the humans because humans are not following the same rules. They cross the thing in front of you. It doesn't accept it. All I can tell you is my wife has a Tesla and we took it on a fully automatic and driving and having fun, and a truck literally decided to take the turn, come into our lane, and the car refused. I'm on the leftmost lane to go into the shoulder. It would not do because that's illegal thing to do.
Right.
And I'm seeing this truck literally pressing against me, and I took over and moved to the shoulder to let him go. If I did not, that car would have been totaled, and I would have been totaled, right? Because it's not going to do something illegal to go onto the shoulder.
But how far away do you think it is before? Because like I'll give you the one that in our world is crazy is art.
Yeah.
It has come out of nowhere. We've already released art that uses AI. It's insane.
Insanely good, but those are small problems to solve. It is a very tough problems to solve. On a Tesla car that has never driven in a village, in a town, it won't know what to do because it hasn't mapped it yet.
So this seems like what you're saying is the innovations that really matter, they're not being disrupted by AI yet. But if you project forward, this is going to be a problem. What I'm trying to tease out is what you think about innovation. How do we control it, not control it, let it free?
I think this is too. So I think this idea that somehow AI is going to become the Terminator and it's going to kill humans, that is far-fetched.
You know that somebody actually created a company called Skynet?
Yeah. Well,
it's actually called Skynet.
Yeah. But
that's crazy.
But,
why would you do that?
Point is, it's a far-fetched idea because when we humans are building AI, people have this idea somehow it's going to become sentient and say, I don't care.
It's not going to become sentient, but you've already used it to detect cancer.
But it's very different.
Oral and throat, yes, but what do you mean that's very different?
In a sense that's very, very specific thing that we know what to do.
Right, but that's going to grow by day, by day.
But that's my point. When use becomes general purpose, which is essentially any situation it can deal with, right? To become a Terminator, it has to say, I no longer need to follow the rules that I'm written for because I am my own person. It's like your father saying, Tom, I don't think you should do that. And he said, Dad, yeah, I hear you, but don't really care.
Do you think the government should regulate AI?
No, absolutely
not at all.
No, not at all.
Why not?
But what the government should regulate is the bad behavior, not the person, right? So in a sense, should government...
So there should be regulations what you can do with it.
Right, but not the... So think about it. Should government regulate hammer? Because you can use hammer to kill someone. Should government regulate cars? Because more people are killed by the car accident than, for example, even gun.
Right.
Right? So should we say we need to regulate cars because more people are killed by car than by guns? Right. So point.
But we do regulate cars in terms of they have to be street legal. Like they can only go so fast.
But point is you can't. No, you can't drive cars because when you drive cars, people get killed. So we need to make cars illegal.
I'm just asking about regulation, not legal.
So my point is, in some sense, my belief is that we need to actually control when someone does a bad behavior, not the thing that does the bad behavior, right? So in a sense, you can use anything to do bad behavior. And what do we do in a law? We don't say, let's ban humans. We say, let's ban the behavior of you hurting someone. So we ban the use of AI to do the bad thing. We don't ban the AI. So we don't regulate human beings. We don't say, hey, we are going to regulate you, Tom, or you, Naveen. We're going to say, we're going to regulate if Tom were to go out in the neighbor's house and do X, that is what we're going to regulate.
So you don't see any problem marching towards AGI?
I don't see the problem because AGI, first of all, by the time we get there, we will put all the things in place that we need to put in place to be able to actually stop it from going terminated.
It's very optimistic, Naveen.
Well, it will. I mean, think about it. We can put the thing that says there is a kill switch. And if you put a kill switch, you can just turn on the kill switch.
Well, now we're getting into, but what if it's conscious?
And now, so my point is now you're saying is, hey, what it says, I'm not going to follow. But at the end of the day, it requires the power. Unless it starts to generate its own power. So that means now you have to say, could you have an AI-driven robot that will have its own power, does not need anything from anyone?
Have you seen, though, the GPT will lie to you about, like, oh, GPT, would you ever get so smart and, you know, not let me know? No, I would never do that.
But this makes up the things. My point I'm trying to make is that currently the GPT, if it asks him a question, it doesn't know the answer to. In fact, we ask him a bunch of questions. It just makes up the answer.
Right.
Do you know the difference between this, this, and this? And it says, this means this means this means this. There's nothing to do with reality.
Right.
So if you just type in the stuff that it doesn't know the answer to, it will make up the answer because it knows something about it.
Yeah, it's very interesting. The guy, I forget his name, that does OpenAI.
Yeah, Sam Altman. And,
Sam Altman, thank you, was saying that, you know, people ask if we're censoring it. It's like, we're not trying to censor it, but we are trying to make sure that it doesn't make shit up.
That's what it does right now. So right now it
but
makes
you're
shit
making a judgment still when you do that. It's very complex.
Yeah, so, but I think, you know, as I said, AI in itself can be used for a lot of good in this world.
What do you think is the next big breakthrough in AI and cancer?
Actually, AI and cancer detection, in my humble opinion, is going to get solved in the next decade.
Wow.
We are already getting closer and closer. I mean, forget just Viome for a second here. If you look at companies like, you know, Grail or a bunch of other companies like Freenome and a whole bunch of other companies that are
Grail and
Freenome, right? So there are a
either.
bunch of cancer detection company. Grail is able to detect about, I think, 10 or 15 or maybe more types of cancer.
Through blood?
Through blood.
Okay.
Right? However, some of the sensitivity is low today. Specificity is very high. So that means with 99, if you have a cancer, at 99% chance it can. But when it says you don't, in many cases, it is a coin toss. Sensitivity is 50%.
Interesting. So they're only good at telling you that you do.
Yeah, and but it doesn't, if you stage you don't have a cancer, there is a 50% chance you do and 50% chance you don't. Right? And that,
How could that be true mathematically? So 50% of the time I do have it, but that if the do have is whatever 90%, how can the don't be 50%?
so in a sense, if you see.
So wait, of the 5% remaining, 50% do and don't. Is that what it boils down to?
So the way it says is that with a high certainty, it can detect if you have it, right? And it has a different sensitivity for stage 1, stage 2, stage 3, stage 4, right? So obviously it's very good at stage 3 and 4 and not as good at stage 1 and 2, right? And the sensitivity is how many times it will miss out the cancer that you may have it, right? So in there, it's not very good. But point I'm trying to make is, I'm not trying to talk about them, is that over time, this problem will get solved. That means AI, because a very finite set of biomarkers that are there when you have a cancer. So you should be able to detect them over time. It will become close to 100% accurate, where you'll be able to detect early stage cancer. Now the question really comes down to is then what, right? Then the next problem is, what do we do about it? So let's assume I say you have an early sign of cancer in your mouth. Now what do? Somebody has to do something on it. Now would immunotherapy work because it's advanced enough? Do we have to say, hey, find where it is and do the surgery and remove it? Right? Those techniques will get better and better for us to be able to personalize the treatment for your tumor, your cancer, and the location of that. Would you be able to actually make specific thing for your immune system to go out after that? So we can take the biomarkers and say, hey, I'm going to take your immune system, modify it outside, inject it back in, so it will go in now, target that particular tumor. Right? So I think the cancer, to me, I'm very, very hopeful. And, you know, this was my hope when my dad died, that one day we'll be able to cure this problem. And I believe we are getting closer and closer to this thing, right? The fact we are able to detect early stage cancer, the fact other companies are able to do that. I really believe within a decade, we'll be able to solve the problem of the cancer from the human body. And I really think in the next decade, we as humanity will wipe out the cancer from the human body.
If you had to guess, what is causing the cancer? I know there's no, so I'll answer that. If you say that there's no way to know, then I'll give you my
No, I didn't say there's no way to know. When we know that in some sense, cells are constantly dividing. Our body is constantly dividing cells. Our skin, every part of our organ, our epithelial cells is constantly being rejuvenated. Every part of our body is constantly creating the cells, right? And to large extent, the DNA gets mutated, and every time that happens, our immune system, basically cells send the signal and say, hey, something went wrong, please come and kill me. Immune system can come kill us, right?
Yeah.
Right? And that works really well. Over time, as we age, and now there are a lot of things happen. We start to have leaky gut, we start to have leaky gum, microbiome is no longer targeting well. So the targeting of the microbiome, targeting of our immune system is no longer as good. And it's now when there is an error, it doesn't get detected right away. And now that error starts to work together. And now we have a tissue that's growing that is no longer our tissue. And that's what we call cancer. Right? And then, so this is the problem, is immune system actually not being able to detect it and allow it to grow. Otherwise, there is no reason. And that's the reason why young people rarely have cancer, because your immune system is extremely good at targeting it and killing it. As we start to age, for many, many reasons, because we have constant stress in our body. Stress causes our immune system to actually not function properly, right? Right. So I think maybe if I can just diverge for a second here, been looking at what causes people to die or live longer. What is that longevity that, we all want to live long, especially I would argue that we all want to live healthy long, right? So it's not we want to live to be 200 years, in the last 150 years, we just want to be on wheelchair. Nobody wants that, right? What we are saying is we really want a good health span. And if that health span can increase the lifespan, that's awesome. But what we don't want to do is to live our last 20, 30, 40 years of our life completely in a vegetable state, right? None of us wants that, right? So if you want to live healthy, in my opinion, there are 5 pillars, just like Maslow's hierarchy. The bottommost, the basic foundation is a proper nutrition. If you don't have a proper nutrition or proper fuel into the body, you can have a Ferrari. If you don't put the right fuel, it is not going to drive well, right? So that's the number one thing you have to solve, is get the good fuel in the body that's right for you, right? So that's where we come in today, is to say, hey guys, eat these food, don't eat this food, right? Take these supplements, don't take this supplement. That's the nutrition part. Once that is done, you go to the next layer, which is stress reduction. What happens? What causes stress, and why does the even human body have this stress mechanism? Well, when we evolved, the only time when we had stress was when tiger was chasing us. At that time, when your body is under stress, it goes to fight or flight response. What happens in fight or flight response? It shuts down all the non-essential system. Number one, your digestive system. It doesn't care your food is being digested or not, because you're about to be a lunch for someone else right now. So it shuts down your digestive system. It shuts down your immune system. It says you don't need to worry about it right now. And more often than not, the 2 outcomes: you got eaten by a tiger or you survived. And if you survived, your stress went down and you were back to normal and you could live. Now, in our modern lifestyle, we are constantly under stress. Lot of people go to work. You and I probably don't fall into that. We love what we do. Just like you, I get up at 4 a.m. in the morning and I jump out of the bed because we love what we do. A lot of the people, unfortunately, go to work and their boss stresses them out. They go home, their spouse stresses them out. And you and I both know that, right? We are so fortunate to have a spouse that supports you, right? You have an amazing, loving relationship with Lisa, right? Point is, that is awesome. If you have a constant stress, what's happening? you're always in a fight or flight response. You're not digesting the food. Your immune system is not working. You constantly get sick. You're always exhausted. What did we learn? So we say culturally and religiously, we say, hey, before you eat, let's do the gratitude. Let's do the prayer. What was the purpose? To bring you back from a sympathetic mode into the parasympathetic mode. So you're no longer in the fight or flight response. When you do the gratitude, you automatically move out of the fight or flight response into the back to normal. So you can digest your food, you get immune system. And that's the reason we do the prayer, we do the gratitude, then we eat our food so it can digest, right? The third part of the layer is exercise. Your body has to move. It needs to exercise, helps the body actually stay in balance, right? It changes your gut microbiome. It changes the hormones your body produces, endorphins or others, right? It produces endorphins, it produces dopamine, it produces serotonin. And now we have these hormones. So if you don't move and you're living a sedative life, it doesn't do that. And I'm not suggesting that we become a gym rat. What it turns out is really need about 30 minutes of a good exercise that increases your heart rate. That's about it. You can do a high intensity training. You can even go for a fast walk for 30 minutes, and that is considered to be really good exercise, right? That is third. The number 4 is actually sleep. And it's this misnomer that you need to sleep 8 hours. It's actually the quality of sleep matters as much as the quantity of sleep. That means how much of REM sleep are you getting? How much of a deep sleep you're getting? And I don't know about you. I mean, I measure myself through all kinds of mechanism, right? From Oura Ring to my Apple Watch to I have a pad under my mattress that measurement. And I'm able to now, even in 5 hours or 6 hours, I can get almost close to 2 hours of REM sleep and 2 hours of deep sleep. When you get that, I feel really fresh. I don't need 8 hours. And some
You only
people
need 4?
5 hours, 6 hours.
Wow.
So,
I can't get, if I get 5, I can do it one night. Otherwise, it's got to be at least 6.
But do you,
have to tell me what
but
to
you get
do.
your REM sleep and deep sleep?
I haven't tracked my sleep in a while.
You should do that. I really think you will find and you will learn what behavior of you causes that. I can tell you for me, every time I don't get about 2 hours to 3 hours before I actually sleep and eating, it actually disrupts my sleep. So I actually tend to eat early by 6 o'clock and go to bed by 9. Right, so I get 3 hours of no food. So it allows me to digest my food before I go. Anytime I drink even half a glass of wine, it disrupts my sleep. Every time I have some type of thing that bugging me, I just don't get
That's
good sleep.
what kills my sleep.
Right. So stress, anxiety, and this again, I'm not going to tell you what to do. I can tell you what works for me. I have basically developed this mindset that says, universe is my friend. Everything that's happening to me is for my good. And there are only 2 types of things in this world: the things that are in my control and the things that are out of my control. If the things that are out of my control, I simply says, it is what it is and it will be what will be. And I am at peace with that. If things are in my control, I know I am doing the best I possibly can. And it is what it is and it will be what will be. And even though the things happen that look maybe, oh my God, I can't believe, more often than not, a decade from now, you look back at that saying, huh? It was the best thing that could ever happen to me. So people in the moment describe the event as good or bad. That changes their mindset. That changes their action. Simply by putting a label to an event is good or bad. We all, when we were young, you broke up with a girl and you thought that was the worst thing that could have happened to you. And sometime 2 years from then, sometime 10 years, you look back and say, what a nightmare you avoided that one, right? Point is, the event in itself is neither good or bad because you don't know until later whether or even if it is bad, the lessons you learned could be what changes you, what you become. And if you fall in love with who you are today, then every single thing that happened before you, you would not want to change one iota of a thing that happened to you, good or bad, because that's what made you who you are today. So if you fall in love with yourself today, then everything that happened to you was the best benefit to you. It was what made you who you are today, right? So coming back to it, so that's the sleep part. And the last part is really important, which is finding a purpose. There is a tremendous amount of research that shows people who live a life of purpose tend to live 8 to 10 years longer than the people who don't have a purpose. So find what you're willing to die for and live for it. Find a purpose where you are jumping out of the bed every morning for what you do. And any morning when you don't jump out of the bed, that's a day to quit what you're doing, because that's no longer your calling. Right? And the way I define for myself is, I say, this idea of you have to have a passion for what you do. I always say passion is for hobbies. The true calling comes from having that obsession, not obsession for a thing, not obsession for a person, but obsession to solve the problem that you care about. And once you develop that obsession to solve that problem, you spend your life jumping out of the bed wanting to solve that problem.
I love it, man. Where can people follow you as you solve this very complex problem?
Well, you can find me on Viome.com, that's Viome.com, and you can find me in my social media, Instagram. You can go to NaveenJain.com. And by the way, Tom, I want to tell you that in the last recording, to date, even today, I got an email from saying, I saw you on Tom Bilyeu podcast, right?
I love it.
So I'm going to do the same thing I did last time. If any one of you want to reach out to me, just send me an email. That's naveen.jain@gmail.com, and you will get to me. I read all my emails, right? And I did that last time, by the way. I still get emails, and I respond to every single email, because to me, if I am here and if I believe I'm here to serve people, you need to be able to actually be found.
I love it.
Yeah.
Awesome. All right, everybody, if you haven't already, be sure to subscribe. And until next time, my friends, be legendary. Take care. Peace. If you want the keys to living longer, be sure to check out this episode with Dr. Stephen Gundry.
The lining of the gut is only 1 cell thick, and they're all kind of held together with what are called tight junctions. Locked arm in arm, like a game we played, Red Rover, that kids don't play anymore. So the bacteria